Okay, that was a little introduction to the song by The Who called Pinball Wizard. And what we're going to be looking at here today is now we get into the calculus of the hyperbolic trig functions. To begin with, I just included the graphs of the hyperbolic cotangent and hyperbolic tangent and the hyperbolic secant, hyperbolic cosecant. You probably don't need to do much with those things. All right, just kind of if you need to look at those for reference, you can, but you don't really have to commit that to memory or anything. All those things could be graphed on the calculator. So if you were going to go back to a couple of pages here where we had the definitions, see, all these things could be put in the calculator for this. So it's pretty easy to get a graph of those things if needed on a calculator, right? So let's see. To begin with, we're going to look at some derivative formulas. Not going to do so much with the integrals in this video, but we're going to focus on derivatives. So it turns out that the derivative of the cosh is the sinh, and the derivative of the sinh is the cosh. Now that's slightly different, of course, than it is in circular trig. So in circular trig, what you would have learned is you would have learned the derivative of the sine is the cosine, but you would have learned the derivative of the cosine is the negative sine. Okay, like that. So it's a little different. Okay, like I said, these things are very similar, but the negatives may be slightly different on these things. So those are the two that you want to really make sure you know, and that's easy to remember. The rest of these can be easily derived, and we're going to talk about that. So derivative of the tanh is the sech squared. Let's see, that's not different at all. The derivative of the tangent of x, you learned, is the secant squared of x. Okay, then we got the derivative of the hyperbolic cotangent is negative cosecant, hyperbolic cosecant squared. It's hard for me to say that sometimes. So in trigonometry, you learned that the derivative of the cotangent of x is negative cosecant squared of x. So that's the same, right? And then you also learned this. In circular, you learned that the derivative of the secant of x is the secant tangent. So see, that's off a little bit. It's off by the negative. The other thing you learned is the derivative of the cosecant of x is the negative cosecant x cotangent x. Now, there's things that not all students catch on to in a trigonometry class. A couple of things I like to mention. This is circular now. So if your trig function begins with a c, and you have a negative answer, okay, I've always just kind of remembered it that way. And then the other thing that's kind of interesting to me is these are cofunctions, right? So tangent and cotangent are cofunctions. Well, so are their derivatives. So they're cofunctions. So if you remember that the tangent is secant squared, which I remember because it shows up a lot, the cotangent does not show up as much. I just remember, well, it starts with c, so it's a negative. And then the cofunction of secant squared is cosecant squared. And then this works the same way. These are cofunctions. Secant and cosecant are cofunctions, so their derivatives are cofunctions. So notice secant, cosecant, tangent, cotangent. So if you've never caught on to that, that's a good thing to know. So really kind of the way I remember this is, of course, I remember that, and I remember this, and I remember that. Those show up a lot, and then the rest of them are cofunctions, right? So you can think of it that way. It's a little bit different with the negatives here on this, so there's some differences that show up on this. So the differences over here is the derivative of the cosine is just the sinh, not the negative sign like it is in circular. These are the same. The derivative of hyperbolic tangent, derivative of hyperbolic cotangent, those are the same. And then what happens on this is a little bit different. The derivative of the sech is negative sech tanh. Okay, everything else is the same. So these are the ones that are different right there. Okay. right? And notice that's cofunctions, cosh, sech, cofunction, not cofunctions, but reciprocal relations, okay? Okay, so you can derive these, so that's what I'm going to focus on the next page is just how to do some derivations of these things. And I'm going to derive the basic ones here and kind of work on that a little bit. Okay, so to begin with, let's start with the sinh. Okay, remember, all you got to know is the definition of the sinh and tanh, or sinh and cosh, and you can derive almost everything else. All right, so let's write down the definition. So that's e to the x minus e to the negative x all over 2. Now what we're going to do is we're going to do the derivative of the hyperbolic sine. So we're just doing the derivative of this, okay? So we're really doing the derivative of, I'm going to write this just as 1/2 e to the x minus e to the negative x, like that, okay? Basic derivative rules. So you write down the constant. The derivative of e to the x is e to the x. The derivative of e to the negative x by chain rule is itself times the derivative of the exponent, which is -1. So see, that's a chain rule. So you end up getting 1/2 e to the x and then what we'd have here is a negative times a negative would be a positive. And then that would be e to the negative x. Okay, so what I did there is, see, I'm doing the derivative of the exponent and multiplying by that negative. Okay, all right, well, what is this? That's the cosh, isn't it? Okay, so that is what the cosh is by definition. So that would show you how to derive that the derivative of the sinh is the cosh. Now, this is an important enough derivative rule that you want to know that derivative rule, so you don't have to derive it, but it is easy to derive. Okay, let's work with the hyperbolic cosine. So the hyperbolic cosine's definition is e to the x plus e to the negative x over 2. So let's do the derivative of the hyperbolic cosine. Okay, so again, I'll write this like this. I'll write this as 1/2 e to the x plus e to the negative x, and then we're just going to do a fundamental derivative. So the derivative, okay, 1/2 is a constant, so just write it down. The derivative of e to the x is e to the x. The derivative of e to the negative x is itself times the derivative of the exponent by the chain rule. So that would be 1/2 e to the x, and then you have a positive times a negative. That would make that minus e to the negative x. Well, what that is that's the sinh definition. So the derivative of the hyperbolic cosine is the hyperbolic sine. Okay, so see, it's actually really easy to do that. So again, what I'm trying to stress is if you know these definitions, you can really figure out just about everything in this section, okay? And that's the way you want to kind of learn this stuff, I think. Okay, next thing I'm going to derive is the hyperbolic tangent. Okay, so let's see. Now I'm going to do this like this. I'm not going to write down the definition of that, although you could. I'm just going to do this like this. I'm going to write down that the hyperbolic tangent by identity is the same as the ratio of the hyperbolic sine to the hyperbolic cosine. Okay, that's the same as circular trigonometry. You learned that the tangent of x is the sine x over the cosine of x. So what we're going to do is we're going to do the quotient rule. So we're going to do the derivative of the hyperbolic tangent of x, and we're going to apply the quotient rule. So the quotient rule, remember, we do bottom times derivative of top minus top times derivative of bottom over bottom squared. So that is the quotient rule. Okay, so let's plug this in, see what we get. So the bottom would be the cosh of x. Then we would multiply by the derivative of the top. And you can do this in your head. You can actually skip this step if you're doing a quick derivation. then it's the top times the derivative of the bottom, and all over the bottom squared, so that would be the cosh squared of x like that. Okay, so that's what we're going to do then. So we're going to do this derivative and that derivative. That's applying the quotient rule. Okay, now what I have is I have the cosh of x. We learned that the derivative of the sinh is the cosh, and we learned that the derivative of the cosh is the sinh. So what we get here is a cosh of x times a cosh of x minus, we have a sinh of x, and then the derivative of the cosh is the sinh, like that, okay? And that would be all over the bottom squared, so that is the cosh squared of x, okay? So what we get then is we get this, okay? We get this, a cosh times a cosh would be a cosh squared x. A sinh times a sinh would be a sinh squared of x. And then we have a cosh squared of x like that. Okay, well, what you got to remember is, what is this? That is the fundamental identity in hyperbolic trigonometry. So we learned that the cosh squared of x minus the sinh squared of x is equal to 1. And just think of this like this. The cosh is the x value, the sinh is the y value. There's the hyperbola, okay? So what we get is we get 1 over the cosh squared of x. So what is that? That is the secant, hyperbolic secant squared of x, or the sech squared of x. So that's how easy it is to derive the derivative of the hyperbolic tangent. In your homework, you'll be doing some derivations. Some of these you'll be just kind of doing on your own and making sure you know how to do those, okay? So all of these can be derived. You could do the derivation of the hyperbolic cotangent in a very similar way to the tangent. Same thing here. Okay, you could write this as 1 over cosh, do a quotient rule to easily derive those. Okay, so I want everybody to know how to derive all of those 6 derivatives of the 6 hyperbolic trig functions then. Okay, now we're going to get into just doing some basic derivatives on this. This hyperbolic trigonometry will show up in some engineering fields, and some of you are going to see that from time to time, and it'll show up a little bit in differential equations too. So we're going to do just some basic derivatives here. So the idea with this is, and I'm going to relate this kind of to what you would have learned how to do in Calc 1. So like if you were doing the derivative of sine 4x, well, this would be chain rule. The derivative of a sine is a cosine. Then you would multiply by the derivative of the function inside by the chain rule, and you would get that. So you're going to do this the same way. So if we do the derivative dy over dx, and you can do this in your head, the derivative of a sinh is a cosh of whatever function, and by chain rule, we always multiply by the derivative of that function that's embedded inside. And you can do that in your head if you want to. So this would end up being cosh of 4x times 4. So we would just write that answer as 4 cosh of 4x. Okay, so that's how you would do the derivative of that. Okay, so all these are going to be pretty similar to what you would do in trigonometry. Okay, so this one right here, the way I'm going to write this is I'm going to write this as the hyperbolic tangent of x squared. Okay, and think about kind of how you would do something like this. If you were dealing with this in circular trigonometry, you would do a chain rule. So y prime on this, what would you do? You would bring down the 2, leave the tangent alone, subtract 1 from the exponent, multiply by the derivative of what's inside, and the derivative of a tangent is a secant squared x. So that's what you would do, and then you might apply an identity to that if you can. So what we're going to do on this, dy over dx here, we're going to do the same thing. You have a function to a power, so do the chain rule. So bring down the 2, leave the hyperbolic tangent alone. That goes to the first power, of course, and then multiply by the derivative of the function inside. Okay, like that. Okay, and you can do that in your head. I'm just trying to carefully write steps. This would be 2 tanh of x, and the derivative of the hyperbolic tangent was the hyperbolic secant squared of x. So see, it's very similar to this, and then that would be a good answer. Okay, you could go a little further with identities. It just sort of depends on the situation and what you're doing with this. So one thing I want to just point up, I want to go up to that list of identities here and show you just one thing here, because we basically derived some of these identities. So here is a useful identity here that we could use. And I'll show you one other thing you could do on this problem. You don't have to necessarily. A lot of this depends on the context of the problem and what you're doing with that. So you could, if there was a need to write this in terms of one trig function, you could write this as 2 tanh of x, and then you could change the sech to 1 minus tanh squared of x. Then you can multiply this out, okay, if you wanted to. Okay, so you can write that in a variety of ways. And actually, that might be a pretty good way to do that if you were working with that derivative in some way then, okay? Okay, so the next one is, let me just kind of review something on this that you would have done in Calc 1. So let's say that you had this instead. You had the ln of some function. Let's just kind of do this in a kind of a simple function like something like this. Okay, well, first of all, the derivative of ln is 1 over the function. So what you learn in a Calc 1 class is the derivative of ln of f of x is 1 over the function times the derivative of the function. That's how the chain rule works for a natural logarithm function. So we're going to do that. We're going to do the 1 over the function times the derivative of the function. So dy over dx should be 1 over the function, which is the sech of 2x, and then we're going to multiply by the derivative of that function inside. Okay, so you're kind of applying a lot of the same rules that you learned in Calc 1. We're just adding the hyperbolic trig functions in here then. Okay, so what we'd have here is we'd end up having 1 over the sech of 2x. Okay, now when you do this derivative, okay, you got to know this rule. We learned that the derivative of the sech of x is remember that one was a negative sech tanh x. Okay, that's what the derivative rule is that we learned there. So that one's a little different. The derivative of a secant is a secant tangent. Derivative of a sech is a negative sech tanh. Okay, it's always so funny when I teach this and say these words. They make me laugh a little bit. So anyway, here's how this goes. So the derivative of this would be negative sech 2x times tanh of 2x. Then you would have to multiply by the derivative of what's inside. So you would be multiplying by the derivative of 2x. So you got to do that, see, all right? So let's just try to kind of put this together now. So what we have here is, and I'm going to put this just in one fraction. So if I multiply this all together, I can kind of think of that all as being over 1. Then I'd have the sech of 2x. And in the numerator, I would have this derivative, of course, would be 2. So I could write this as negative 2 sech of 2x times tanh of 2x like that. Okay, so that's what I'd end up having. And then what's going to happen is, notice that those will divide out. So what we would have as a simplified derivative would be negative 2 tanh of 2x. All right, and that would be as far as you can take that derivative down like that then. Okay, so that's as far as we're going to do that. Okay, all right. So this one now, we're going to go back to just some of the simpler derivative rules we did. This is a product rule here. So when you're doing this one, you got two functions. So just say, for instance, you had x squared times the cosine of 3x squared. Okay, this would be like something you would do in Calc 1. The product rule, sometimes I do that backwards of what some students are taught. I think of this as the first and the second, and the product rule, I go first times derivative of second plus second times derivative of first. Sometimes a textbook, and I think our textbook just shows, do the derivative of first times the second, and then plus the derivative of the second times the first. Well, it's all the same. It doesn't matter which way you do that. I think I was probably taught this way, and I'm so used to doing it that way. That's how I do that, but it doesn't matter because you're doing the same thing anyway. So on this one, I'm going to do the derivative dy over dx. So my first is x to the second. Then I'm going to multiply by the derivative of the second. Now I'm going to write that as the hyperbolic cosine of 3x, the whole thing squared. And then plus, then I'll do it backwards, then I do the second function, which I'm just going to write as the hyperbolic cosine squared 3x, and then times the derivative of the first, x squared. Okay, let me get rid of some of this stuff that's in the way here. All right. So anyway, I'm kind of applying this derivative formula right here. So that's now been set up in the product rule. What I did is first times derivative of second plus second times derivative of first. So let's work that out and kind of see where it leads us. Okay, so if I do this, I'll end up having x squared. This part right here is a chain rule. So this is going to go like this. Bring the 2 down. Okay. So I'm just going to bring that down. So I'll bring the 2 down, and then this stays the same. So I would have hyperbolic cosine of 3x, all to the first power. Then I've got to do the derivative of what's inside. Now, you're welcome to do that in your head. As I'm teaching this, I'm going to try to fairly methodically write those steps. Okay, so we're going to do the derivative of what's inside by the chain rule. Then over here, I write down the second, which is the cos squared of 3x. Then when I do the derivative of the second, okay, I can do that in my head. That's going to be times 2x. Okay, so that's what I've got there then. All right. So now what I'm going to do is I'm going to work on this derivative, just kind of bring everything down, and then we'll see what kind of simplification I can do. So this would be 2x to the second, hyperbolic cosine of 3x. The derivative of a cos is a sinh. So this part right here is going to be the sinh of 3x. But then you got to, by chain rule, multiply by the derivative of what's inside. So that's a 3. And then all this stuff we're done with. So I'm just going to bring that down and write that as 2x hyperbolic cosine squared of 3x like that. Okay, so I do that. And that right there is my derivative. I just need to clean it up a little bit. So over here, I see I have a 3 and a 2. So I'm going to write that as 6x to the second. And then I have hyperbolic cosine of 3x. And then I have hyperbolic sine of 3x also. And then over here, I can bring this down like this. So that is 2x hyperbolic cosine squared of 3x like that. And then I can factor. Typically what you want to do on derivatives is factor if you can. So there's a couple of things I see. I can take a 2x out. And the other common factor it looks like I have here is a hyperbolic cosine. So if I factor this out, I'm going to take a 2x out, and I'm going to take one of the hyperbolic cosines out like this. Okay? So I just kind of go multiply backwards in your head. I need to multiply 2 by 3 to get 6. I'll multiply x by x to get x to the second. And then I also need a sinh in there. So I'll have a hyperbolic sinh of 3x. Just make sure that checks out. And then 2x times 1 is 2x, but I just need to multiply the cosh by a cosh to get a cosh squared. Okay, like that. So that would be, oh, I didn't mean to do that. That should be a cosh. There we go. Okay. So that right there should be a good way to write that answer is in a factored form like that. Okay, so the calculus part of this, what you're mostly going to be doing in this part is just practicing some derivatives. The derivative skill mostly is developed in Calc 1, but you're just learning those new derivative rules for the hyperbolic functions. So that's all I'm going to do on this video is just the derivative part. Then I'll do the integral part next.